In the silent dark, a city-sized corpse spins 700 times every second. One spoonful of it weighs more than every human on Earth combined. Touch its surface, and you would be crushed thinner than paper before you finished blinking. Tonight we travel to objects so extreme they barely seem real. Stars made of nothing but neutrons, magnetic fields strong enough to rip atoms apart from thousands of miles away, collisions that forge the gold in your jewelry, mountains the height of a coin that release more energy than the sun. If wonders like this keep you up at night, hit that like button and subscribe so you never miss a journey into the impossible. Prepare yourselves. We begin. Somewhere in the galaxy, right now, a giant star is running out of fuel. For 10 million years, it has burned hydrogen, then helium, then carbon, stacking heavier and heavier elements in its belly like layers of an onion. Tonight, that onion reaches iron, and iron is where everything ends. Iron cannot release energy by fusing. The fire that held the star against its own crushing weight simply switches off. In 1/4 of a second, the core stops being a star and starts being a falling building the size of a planet. Picture something as wide as Earth, shrinking to the size of a city in less time than it takes you to blink. The collapse moves at roughly 1/4 the speed of light. Atoms are squeezed so violently that electrons get rammed into protons, and the two fuse into a third thing entirely: neutrons. Trillions upon trillions of them, packed shoulder to shoulder until they refuse to move another inch. That refusal is what saves the corpse from becoming a black hole. The neutrons hit a wall called degeneracy pressure, a quantum rule that says no two of them can occupy the same state. The collapse slams to a stop. The outer layers of the star, still falling inward at thousands of miles per second, hit this suddenly rigid core and bounce. What happens next is one of the most violent events in the universe. A shock wave rebounds outward through the star, carrying the energy of 100 billion suns. For a few seconds, this single dying star outshines its entire galaxy. We call it a supernova. From 1,000 light years away, you would see a new sun appear in the sky bright enough to read by at midnight. But the supernova is only the curtain falling on the real show. The real show is the thing left behind in the center, a sphere about 12 miles across, roughly the width of San Francisco. Inside that sphere is more mass than our entire sun. More than 300,000 Earths squeezed into something you could drive across in 20 minutes. This is a neutron star, and it has just been born. In its first moments, it spins. Anything that collapses tightens its rotation, the same way a figure skater pulling in her arms whirls faster. The original star may have turned once a month. The neutron star can turn hundreds of times every second. Its surface, if you could stand near it, moves at a fraction of the speed of light. It is also unimaginably hot, around 1 trillion degrees Fahrenheit in its first instance, hotter than the core of any normal star, so hot that the visible light pouring off it is almost an afterthought. Most of its energy escapes as ghost particles called neutrinos, which slip through solid matter as easily as sunlight slips through glass. The supernova fades over weeks, the sky darkens, the expanding gas cloud thins out, and in the middle of it all sits this tiny vicious survivor, cooling by only a few degrees per year, ready to last almost forever. Almost, because what lies on the crust of this newborn is something so strange that physicists had to invent a new word just to describe it. A type of matter that should not exist anywhere in nature, yet sits inches beneath the surface of every neutron star ever born. The crust comes next. But first, you have to understand what you would be holding if you could reach down and scoop a single spoonful off the top. Imagine standing in front of a kitchen drawer. You take out an ordinary teaspoon, the kind you stir sugar with. Now imagine filling it, just to the rim, with material taken from a neutron star. Nothing fancy. No deep coring, just the stuff sitting on the very surface. That spoonful would weigh about 1 billion tons, Stop and let that number find its shape. 1 billion tons is roughly the combined weight of every human being alive on Earth right now. All 8 billion of us, every man, woman, and child, every newborn, every grandparent, compressed into a volume small enough to balance on your pinky finger. Or think of it this way. Mount Everest weighs around 160 billion tons. A neutron star teaspoon weighs about 1/160th of Mount Everest, crushed into a sugar cube. The number is so absurd that physics teachers love to repeat it. But the deeper question is how? How does matter get this dense? The answer is that down there, atoms have given up. Everything around you, your chair, your hand, the screen you might be looking at, is mostly empty space. If an atom were blown up to the size of a football stadium, the nucleus would be a marble at the center. Everything else is just electrons buzzing in a vast emptiness. The reason your hand does not pass through the table is that the electrons of your hand push against the electrons of the table, not the atoms themselves, just the buzzing fields around them. Inside a neutron star, that empty space is gone. The gravity is so brutal that electrons have been crushed into the nuclei. There are no atoms anymore, only neutrons, stacked against each other like coins in a roll, with almost no gap between them. Now imagine trying to lift that teaspoon. You could not. Even with the strongest crane ever built, you could not lift 1 billion tons. But more importantly, you could not even bring the spoon up to the surface in the first place. As soon as that material left the gravitational vice of the neutron star, it would explode. Without the crushing pressure holding it together, the neutrons would spring apart with the force of a small nuclear bomb. A spoonful of neutron star, brought to Earth, would erase the city around you. This is matter that exists nowhere else in nature, not in our cores, not in the sun, not even in the centers of giant planets like Jupiter. To find it, you have to go to a place where gravity has won the war against everything else. Density like this changes what you see, too. A neutron star is so small and so massive that its gravity bends the light coming off its own surface. You actually see slightly around the back of it, like peeking over a hill that does not exist. More than half the surface is visible from any angle. That same gravity does something stranger to the matter just below the crust. Something physicists describe by reaching for words from an Italian kitchen. A few hundred feet beneath the surface of a neutron star, the laws of chemistry break down, and something stranger takes their place. Physicists gave it a playful name because the shapes look like the contents of a kitchen pantry. They call it nuclear pasta. Down there, neutrons and the few remaining protons cannot exist as round, friendly clumps anymore. The pressure stretches them. It bends them. It forces them into long tubes, like uncooked spaghetti. A little deeper, the pressure flattens those tubes into sheets, like layers of lasagna. Deeper still, the sheets curl into shapes that look like bow-tie pasta or honeycomb-shaped gnocchi. There is even a layer affectionately called Swiss cheese, where bubbles of empty space float inside a sea of solid neutrons. This is not a metaphor invented for fun. Computer simulations using the actual equations of nuclear physics keep producing these exact shapes. The math demands them. Matter under that kind of squeeze stops looking like matter and starts looking like a dinner menu. Now, here is the part that should make your skin tighten. Nuclear pasta is believed to be the strongest material in the universe. When scientists tested its strength on supercomputers, they found it is roughly 10 billion times stronger than steel. Imagine a sword forged from nuclear pasta. You could cut through a mountain and the blade would not even scratch. You could stab a battleship and pull it out clean. Nothing we have ever built or measured comes close. The carbon nanotubes that engineers dream of for space elevators are weak by comparison. Diamond is weak by comparison. Bone, Kevlar, titanium, all of them dissolve in the imagination next to a single strand of neutron star spaghetti. So why does this matter beyond being a wild fact at a dinner party? Because that incredible strength does something visible from across the galaxy. The crust, locked together by these pasta layers, can hold a neutron star in an almost perfectly smooth shape, even while it spins hundreds of times a second. Any other material would be torn apart by that kind of force, the way a clay vase on a fast pottery wheel splatters across the room. Nuclear pasta holds. Until it does not. Sometimes the spinning slows ever so slightly, or the magnetic field tugs in just the wrong way, and the stress on the crust becomes too much even for pasta to bear. The shell cracks, and when something 10 billion times stronger than steel cracks, the energy released is staggering. We will return to those quakes later, because they deserve a chapter of their own. For now, picture this: a sphere the size of a small city, with a thin solid crust no thicker than a few hundred yards, sitting on top of layered tubes and sheets of pure neutrons. Beneath those layers, the matter gives up its last familiar shape and becomes a sea of free-flowing neutrons behaving like a fluid, with no friction at all. A liquid that once stirred would keep flowing forever without slowing down. That is just the inside of the star, sitting quietly. The truly violent part of a neutron star reaches outward into space, invisible to your eyes, but powerful enough to twist the very atoms of any unfortunate spacecraft that wandered too close. And on some neutron stars, that invisible force is so extreme it has its own name. Step away from the crust for a moment. Put yourself in a spacesuit, a very durable one, the kind that exists only in fantasy, and drop yourself, feet first, toward the surface of a neutron star from about 1 mile up. You would never reach the ground. The gravity at the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel right now. 200 billion. Your bathroom scale would not read a number. It would simply vaporize. That kind of pull does things to a human body that the word death does not quite cover. As you fall, your feet are closer to the center of the star than your head. Even that small difference, just 6 feet, means your feet experience a much stronger tug than your head. The result is that you are stretched, not slowly, violently. Astrophysicists have a name for it. They call it spaghettification, the same word that gets used near black holes. Long before you reach the surface, you are pulled into a strand of atoms, a few atoms wide and miles long, screaming toward the crust at a significant fraction of the speed of light. You would hit the surface harder than any meteorite that ever struck Earth. The impact energy of a single human body landing on a neutron star would rival a small nuclear weapon. You, the spacesuit, all of it, would flash into raw energy in less than a millionth of a second. The neutron star would barely notice. It might gain a fraction of an ounce. The geometry of light around the surface is just as strange. Because the gravity is so intense, light cannot travel in straight lines near the star. It bends. A beam of light shot sideways, parallel to the surface, will curve and orbit the star several times before flying off into space. This means that if you somehow stood on the surface and looked at the horizon, you would not see a horizon at all. You would see the back of your own head. The light leaving the front of your face would loop around the entire star and return to the back of your eyes. The whole sky would appear compressed into a tiny circle directly overhead, with the rest of your view filled by the curved surface stretching impossibly far in every direction. There is also a strange consequence for any clock you brought with you. Time itself slows in a strong gravitational field. On the surface of a neutron star, time runs about 30% slower than it does back on Earth. If you stood there for what felt like 7 minutes, 10 minutes would pass for your family at home. Not enough to be useful for time travel, but enough to be deeply unsettling. A radio signal you sent up to a friend orbiting nearby would be stretched, its frequency dropping, its pitch lowering, as if the whole conversation were being dragged in slow motion. All of this happens on the calmest, oldest neutron stars, the ones that have settled into a quiet rotation, cooled for millions of years and stopped throwing tantrums. The young ones are far worse. The young ones have something extra, something that wraps around them like an invisible storm, and reaches out into space for thousands of miles, twisting reality on a scale that makes the surface seem almost gentle. Most neutron stars have magnetic fields. Even the calmest of them carries a magnetism roughly 1,000,000,000,000 times stronger than the magnet on your refrigerator. That alone is enough to scramble any electronic instrument we have ever built. A small group of them are different. We call these magnetars. They are the rarest, angriest, most dangerous objects in the known universe. A magnetar's magnetic field is about 1,000 times stronger than a regular neutron star's, which means it is roughly 1,000,000,000,000 times stronger than Earth's magnetic field. Numbers that large stop meaning much, so try this instead. If a magnetar drifted to within half the distance of the Moon, it would erase every credit card on Earth, every hard drive, every phone, every laptop, every pacemaker, every car battery. The magnetic strip on the back of your driver's license would forget what it ever knew. If it came within roughly 600 miles of you, the field would start to rearrange you on the chemical level. Atoms become distorted. Electron clouds stretch into thin cigars. Water molecules in your body would no longer behave like water. The chemistry that keeps you alive simply stops working. You would not be killed by force or radiation. You would be killed because your atoms can no longer remember how to be themselves. This is matter being unmade by a magnetic field. Nothing on Earth in any laboratory can come close to producing such a force. Our strongest sustained magnets clock in at roughly 45 Tesla. A magnetar can hit 100 billion Tesla. The gap is so wide that it stops being a comparison and starts being a different category of physics altogether. Astronomers have only confirmed around 30 magnetars in our entire galaxy. They are rare because their magnetic fields are so violent that they burn through their own energy in just a few thousand years. By cosmic standards, they live a heartbeat and then go quiet, demoted to ordinary neutron stars or fading silently into the dark. But while they are active, they put on a show. In December of 2004, a magnetar called SGR-1806-20 released a burst of gamma rays so powerful that for 1/5 of a second, it outshone the full moon in our sky. The magnetar was 50,000 light-years away on the far side of the Milky Way, behind a dense fog of stars and dust, and it still flooded our upper atmosphere with enough radiation to compress part of it inward and disrupt radio signals around the planet. If that same burst had happened from within 10 light-years of Earth, it would have stripped our ozone layer in a single instant. The food chain would have collapsed within months. Astronomers later realized that something similar may have caused a mass extinction in deep prehistory, though that remains a theory, not a confirmed fact. Every magnetar is a ticking weapon aimed at no one in particular. They flicker on for the briefest of stellar lifetimes, hurl their tantrums across the cosmos, and then vanish back into the population of quiet, ordinary spinning corpses. Most of those corpses tick along with the precision of a metronome, which is what makes it so unsettling when, every once in a while, one of them suddenly speeds up for no reason anyone fully understands. Take a neutron star that has settled into adulthood. It is not a magnetar. It is not throwing fits. It is just a city-sized object, spinning steadily in the dark, completing dozens or hundreds of rotations every second. We have been watching some of them since the 1960s, and they are the most reliable clocks in the universe. More accurate than your wristwatch. More accurate than the atomic clocks in your phone's GPS. Some of them keep time so well that astronomers can predict where the pulse will arrive on Earth with an error of less than 1/1,000,000th of a second over a decade. And then, for no obvious reason, one of them speeds up. Not slows down, which would make sense. A spinning object loses energy. It should be braking gently, drifting towards stillness over millions of years. Instead, every now and then, a neutron star takes a tiny, sudden leap. Its rotation rate jumps faster in an instant. We call it a glitch. It looks like a watch that ticks once at exactly the wrong moment, then settles back into rhythm. Astronomers first spotted glitches in the Vela pulsar, a young neutron star in the southern sky, back in 1969. Since then, glitches have been recorded in dozens of pulsars. Some of them glitch every few years, some glitch only once in a lifetime of observation. And the question of why is still open. The best guess involves what is happening beneath that thin crust. Remember the layers underneath. Below the pasta, the inside of a neutron star is mostly a sea of free-flowing neutrons behaving as a superfluid. That superfluid does something bizarre. It does not slow down with the crust. The crust, which we can see, is breaking gradually. The superfluid inside, which we cannot see, is spinning at its own pace. Over time, the two get out of sync. The inner ocean spins faster than the shell. For a while, the two stay coupled by thin threads, almost like cobwebs of energy linking the inside to the outside. But the stress keeps building. And then, somewhere down there, the cobwebs snap. The inner superfluid suddenly transfers its momentum to the crust. All at once, the whole star jumps forward. The surface speeds up. The glitch is recorded by some patient radio telescope on a planet thousands of light years away. That is the leading theory. It still has holes. Some glitches are too big to explain with simple coupling. Others happen in stars too cold to have the right kind of superfluid, at least according to current models. The glitches are like the heartbeats of an alien creature, whose biology we are still trying to read. There is also a darker possibility. Some glitches may not be smooth internal shifts at all. Some may be quakes, real cracks in that nuclear pasta crust, releasing energy in ways that nudge the entire star. When that happens on the largest scale, it stops being a glitch and starts being something else entirely. A starquake, the same kind of event that has been linked to gamma-ray bursts, brighter than entire galaxies. But before we get there, there is another flavor of neutron star to meet. One that ticks not dozens of times a second, but 700. A star that has been spun up by feeding on a neighbor like a parasite in slow motion. Most pulsars rotate somewhere between once a second and a few dozen times a second. Fast, but imaginable. You can almost picture a lighthouse spinning that quickly, a beam sweeping past your eyes once or twice with each blink. Now picture a city-sized object turning 716 times every second. That is the rotation speed of PSR Joan 748. 2446AD, the fastest spinning neutron star ever confirmed. Its surface at the equator moves at roughly a quarter of the speed of light, around 46,000 miles per second. If it were the size of Earth and spinning that fast, the planet's equator would be flung apart in less time than it takes for the question to leave your mouth. But this neutron star holds together. The same gravity that crushed it into existence is strong enough to keep its surface gripped tightly even against that screaming rotation. Nuclear pasta in the crust takes the strain. The star spins like a top, undisturbed, completing more rotations in 1 second than a car wheel does on the highway in a minute. These ultra-fast neutron stars have a nickname, millisecond pulsars, because each rotation lasts only a few thousandths of a second. The first one was discovered in 1982, and it puzzled astronomers immediately. Neutron stars are supposed to slow down with age. The galaxy is full of older pulsars rotating once every few seconds, like sleepy grandfathers. So how did some of the oldest known neutron stars end up spinning faster than the youngest ones? The answer turned out to be a story of slow theft. Millisecond pulsars almost always have a companion, a second star, ordinary or dying, orbiting close. Over millions of years, the neutron star's gravity pulls gas off the surface of its partner. That gas spirals inward, forming a glowing disk, and as it falls onto the neutron star, it carries its rotation with it. Every drop of stolen matter gives the neutron star a tiny push, like a hand spinning a top. Over time, the pushes add up. The neutron star, once slow and aging, gets recycled. It spins faster and faster, drinking down its companion until the partner is a husk. Some companions are completely consumed. The neutron star is left alone in space, still spinning at hundreds of times per second, a kind of cosmic vampire whose meal walked away with nothing. Astronomers call this process recycling, and they call the resulting pulsars recycled pulsars. The names are dry. The reality is anything but. We are watching one dead star eat another in real time with telescopes that can clock the rhythm down to a fraction of a microsecond. Here is the part that pushes into the realm of pure imagination. The current speed record is 716 rotations per second. Theoretical work suggests neutron stars could possibly spin even faster, perhaps up to 1,000 or 1,500 per second, before they would start to fly apart. Somewhere out in our galaxy, one might be turning right now near that limit, hidden in dust. Its pulse is too fast or too faint for us to have caught yet. When we do catch their pulses, we see something strange. A beam, like a searchlight from a coastline, sweeping across the sky and tagging us once with each rotation. That beam has its own story. In 1967, a graduate student named Jocelyn Bell was looking through long strips of paper printout, the kind that recorded radio signals from a telescope in England. She noticed a tiny irregularity, a signal repeating, with strange precision, exactly every 1 1/3 seconds. It was so regular that her team briefly wondered if it might be a message. They half-jokingly labelled it LGM-1, short for Little Green Men. They were not serious. But for a few weeks, no one had a better explanation. What Jocelyn Bell had found was the first known pulsar. The signal was not a message, it was a lighthouse. Every pulsar is a neutron star with a powerful magnetic field that is tilted relative to its spin axis. Picture a globe spinning on a tilted stick, like Earth's axis, but with two bright beams shooting straight out of the magnetic poles. As the star rotates, those beams sweep through space, carving cones of radiation. If one of those cones happens to point at Earth as it sweeps past, we see a pulse, then another, then another. Hundreds of millions of years of perfect clockwork. Most pulsars only flash radio waves. Some flash visible light, or X-rays, or gamma rays. A few flash in all of them at once. The Crab pulsar, sitting in the heart of a famous gas cloud about 6,500 light-years away, blinks 30 times a second across the entire electromagnetic spectrum. If you could see in radio waves, the night sky over Earth would be flickering with hundreds of tiny strobe lights from across the galaxy. The strange part is what those beams actually are. They are not flashlight beams. They are columns of charged particles, mostly electrons and positrons, being whipped along magnetic field lines at speeds very close to the speed of light. Where those field lines bend, the particles dump their energy as radiation. The whole assembly is a particle accelerator the size of a city, running on the magnetic muscle of a dead star. Here is the part that should give you a shiver. A pulsar's beam might point at Earth, or it might not. A neutron star can be sitting in a nearby patch of space, fully active, screaming pulses out into the universe, and we would never know because its beams happen to be aimed in other directions. Statistical estimates suggest there could be tens of millions of neutron stars in our galaxy, but we have only detected a few thousand. The rest are dark to us, not because they are silent, but because their lighthouses do not happen to sweep over our pale blue speck of a planet. Imagine standing on a foggy coast at night, knowing there are thousands of lighthouses out at sea, but only able to see the ones that happen to flash in your direction. That is what mapping pulsars feels like. There is one more twist. Pulsar beams are so reliable that scientists already use them. By timing how their pulses arrive at Earth, astronomers can detect tiny wobbles in our solar system caused by gravitational waves passing through. They can also use sets of known pulsars as a kind of cosmic positioning system, which we will come back to later when we talk about leaving the solar system. But before we head outward, we have to look at the surface again, because something is sticking up from it, something that is, technically, a mountain. The word mountain calls up Everest, or the Rockies, or that ridge somewhere in your country that takes a day to hike. A neutron star has mountains too. But they are not what you think. A neutron star mountain is, at best, a fraction of an inch tall. The tallest neutron star mountain ever theorized would barely reach the height of a coin standing on its edge. Most are even smaller, just a few millimeters above the otherwise nearly perfect sphere of the crust. Some may be no taller than a grain of sand. This is not because the crust is too weak to support height. It is because gravity is too strong to allow it. 200 billion times Earth gravity flattens everything. Anything that tries to rise more than a few millimeters above the rest of the surface gets pulled back down with crushing force. To build a mountain on a neutron star, the strength of the crust has to win against that gravity. And here, finally, that nuclear pasta does something interesting. Because it is 10 billion times stronger than steel, the pasta crust can actually hold up tiny mountains. They are real, they are solid, they have shapes. They just live in a world where the difference between a tabletop and a mountain peak is less than the thickness of a human hair. Now, why does any of this matter? Because if a neutron star spins, and it is not perfectly smooth, that tiny lump becomes a beacon for one of the most exotic signals in physics: gravitational waves. When a spinning object has a bump on it, it stirs the fabric of space and time, sending out ripples. For a perfectly smooth neutron star, those ripples would be too faint to detect. For a spinning neutron star, with a mountain just a few millimeters tall, the ripples might just be within reach of our most sensitive instruments. For years, gravitational wave detectors on Earth, like LIGO and Virgo, have listened for these signals. So far, no neutron star mountain has been directly heard. But the search continues. If we ever do detect that hum, it would mean we are essentially measuring a city-sized object by the height of a pebble on its surface, from thousands of light years away. There is also a darker consequence. The bigger the mountain, the more gravitational waves the star radiates, and the more its spin slows down. Some scientists believe that the reason millisecond pulsars cannot quite reach the theoretical maximum spin speed is exactly this. As they try to spin up by stealing matter from a companion, the very accumulation of mass forms little hills on their surfaces, which then radiate gravitational waves, which then drag them back down. A built-in brake made of dead matter. So picture this: a sphere of city-wide size, spinning hundreds of times per second, with a bump no taller than a sesame seed, slowly bleeding away its energy into the very fabric of space. The mountain is invisible, the energy loss is invisible. The neutron star itself is, by our standards, almost invisible too, and yet the entire universe is being subtly disturbed by it. Beneath the mountains, the temperature tells another story. A neutron star is born hotter than any laboratory could ever recreate, and the way it cools is one of the slowest, longest deaths in nature. A neutron star, in its first seconds of life, sits at around 1 trillion degrees Fahrenheit. The Sun's core, by comparison, is a chilly 27 million. That means a newborn neutron star is roughly 40,000 times hotter than the heart of our local star. You would think something that hot would blaze across the sky. It does, in a way, but almost all that heat escapes invisibly. In those first moments, the neutron star is so hot and so dense that ordinary photons, the particles that make up light, cannot easily push their way out. They get trapped in the crushed matter, scattering against neutrons over and over. The radiation we usually associate with hot objects, the warm orange glow of a stove element, has nowhere to go. Instead, the heat leaks out in a different form: neutrinos. Tiny, near-massless particles that almost never interact with anything. They pour out of the newborn neutron star by the trillion, slipping through its dense layers as if the entire 10-mile-wide object were not even there. In the first 10 seconds of a neutron star's life, it releases more neutrinos than the Sun has emitted in its entire existence. About 99% of the energy of the original supernova explosion is carried away by these ghost particles. The dramatic flash of light we see from across the galaxy is just one tiny percent of the actual energy released. When scientists detected neutrinos from a supernova called SM 1987A in a nearby galaxy, they caught about 24 neutrinos in total. 24 out of an absolute flood. That tiny handful was enough to confirm the entire theory of how neutron stars are born. After the first frantic minute, the cooling continues, but it slows. Once the neutron star drops below about 10 billion degrees, the neutrino flood weakens and ordinary thermal radiation takes over. The star begins to glow softly in X-rays. This is the part that surprises people most. A neutron star born screaming hot will spend the next million years still being hotter than anything humans can build. Even after a million years of patient cooling in the empty dark of space, its surface is still around 1,000,000 degrees Fahrenheit. Touch it then, if you could find a way, and you would simply cease to be matter. After tens of millions of years, the neutron star finally settles into something resembling a comfortable temperature. Comfortable, in this case, meaning a few thousand degrees, hotter than a forge, but no longer dangerous to view from any distance. And here is the kicker. We have never seen a neutron star get cold. They live so long and cool so slowly that none of the ones we observe today have had time to fade. The universe is not old enough yet. The first neutron stars ever born, somewhere in the early dark after the Big Bang, are still warm, still glowing softly, still ticking out their patient pulses, or sitting silently in some far corner of a galaxy, a fire that refuses to die, a clock that may outlast every black hole, every galaxy, every form of matter we currently understand. And inside that slow, stubborn glow beneath the crust, beneath the pasta, beneath the sea of neutrons, lies something that might not even be neutrons anymore. Drill in your imagination deeper than the crust, past the strange pasta layers, through the ocean of free neutrons, down to the very center of a neutron star, where the pressure is highest and the rules of normal matter have already broken twice. The question is whether the rules might break a third time down there. Some physicists think they do. Inside every neutron, 3 smaller particles are packed together. They are called quarks, 2 of one kind, called down quarks, and 1 of another, called an up quark. Quarks are usually shy. They never want to be alone. The strong nuclear force binds them so tightly that under normal conditions, you can never see a quark by itself. Try to pull one out of a neutron, and the energy you spend ripping it free just creates new quarks to keep it company. But what if the pressure in the core of a neutron star is high enough to overcome that shyness? Then the neutrons themselves would dissolve. Their boundaries would melt. The center of the star would no longer be a sea of neutrons, but a sea of free quarks, swimming together in a soup that has no nuclei, no protons, no familiar matter of any kind. We have a name for this hypothetical state. It is called quark matter, and a star whose entire core is made of it is called a quark star. A quark star is even denser than a normal neutron star, smaller too, and it would behave slightly differently. Its surface gravity might be tweaked, its cooling might follow a different pattern, its quakes might release energy in unfamiliar ways. The problem is, from the outside, a quark star can look almost identical to a regular neutron star. The differences are subtle. You would need extremely precise measurements to tell them apart, and most of our neutron stars are too far away for that. There is a candidate, an object called RX-Joan 8565 3754, sitting about 400 light-years from Earth. It is the closest known neutron star to our planet, and by some measurements, it appears to be smaller than a neutron star should be at its mass. Some scientists have suggested it might actually be a quark star, or at least a hybrid with a quark core. Other scientists say the data is not strong enough yet. The debate is open. This matters because it would mean we are looking at a brand new state of matter. Not gas, not liquid, not solid, not even neutron pasta. A liquid sea of free quarks, glued together by forces we can only study at the largest particle accelerators on Earth. For vanishingly short instants, in a neutron star core, that state could exist for millions of years. There is an even wilder idea. Some scientists have speculated that quark matter, once formed, might be the true ground state of all matter. Meaning, if you could touch a quark star with ordinary matter, the ordinary matter might convert into quark matter on contact, like a rust that spreads. This is called the strange matter hypothesis, and it is unconfirmed. It might be a fantasy. It might also be the most important rule of physics that we have not yet caught. What we do know is that when two of these dense corpses meet, what happens next can rewrite the periodic table. Sometimes neutron stars are born in pairs. Two giant stars orbiting each other both blow up as supernovae and leave behind two neutron stars that keep circling, locked in a gravitational dance. They spend hundreds of millions of years orbiting in near silence. Slowly, they spiral closer together. Each orbit is a hair tighter than the last. Each year shaves a tiny distance off the gap between them. This spiraling is not friction. It is gravity itself bleeding away. Two dense bodies orbiting each other shake the fabric of space, and those shakes carry off energy. Without that energy, the orbit cannot stay wide. The two stars fall toward each other by inches per year, then yards per year, then miles per year, then thousands of miles per second. And then, in the final 100 seconds of a billion-year courtship, everything happens at once. The two neutron stars whip around each other faster and faster, hundreds of times per second, in their last moments. They are now closer to each other than your hand is to your face. Tidal forces start to peel the crusts apart, flinging gobs of neutron-rich material into space. When they finally touch, they do not bounce. They merge. Two dead cities of compressed matter collapse into one, possibly forming a brief, hypermassive neutron star that staggers for a few milliseconds before either stabilizing or collapsing into a black hole. The full crash unleashes more energy than any other event in the modern universe, except the merger of black holes. The light show is staggering. We call it a kilonova. For a few weeks, the merger site glows brighter than 1 billion suns, fading through colors as its expanding cloud cools. And the matter ejected from those last desperate moments is where things get truly personal. Inside that cloud of debris, free neutrons crash into atomic nuclei at high speeds. They get absorbed. The nuclei become heavier. They decay. They become heavier elements. In a single afternoon, the merger forges gold, platinum, uranium, the rare metals that take billions of years to build through normal stellar processes get manufactured in a handful of seconds in a violent stellar collision. Most of the gold on Earth, the gold in your jewelry, the gold in your phone, the gold in dental fillings, was created in events like this, not in supernovae, not in our sun. In ancient neutron star mergers that happened long before Earth even existed, the debris from those collisions floated through space for millions of years, mixed into the cloud of gas that eventually formed our solar system, and got baked into the rocky young planet we now call home. When you put on a wedding ring, you are wearing the leftovers of a collision between two of the densest objects in the universe. In 2017, astronomers detected one of these mergers in real time. The event was named GW170817. They saw the gravitational wave signal from the spiraling. They saw the gamma ray burst from the impact. Telescopes around the world swung onto the same patch of sky and watched the kilonova fade over weeks. And in the chemical fingerprints of that fading light, they detected heavy elements being made in front of their eyes. It was the first time humans had ever watched the universe build gold from scratch. The kilonova is the visible echo of a merger, but its story keeps reaching outward in space and time. A single neutron star collision can be detected from billions of light-years away, brighter for a moment than entire galaxies. The name kilonova comes from its brightness. About 1,000 times brighter than a nova, the kind of stellar outburst astronomers had been studying for centuries. It is dimmer than a true supernova, but its colors and its chemistry are completely different. A supernova flash is mostly light from explosive carbon and oxygen burning. A kilonova flash is sunlight bouncing off a freshly minted cloud of the heaviest elements in the periodic table. Picture the moments after the merger. Two neutron stars have just become one. The new object, whatever it ended up as, is screaming with energy. Around it, a donut of hot debris spins out at 20% of the speed of light. This debris is rich in raw neutrons, so heavy with them that any nucleus floating in the cloud gets bombarded by tens of neutrons at once. Each absorption pushes the nucleus up the periodic table, from iron to silver, from silver to gold, from gold to platinum, from platinum to uranium. The process happens in seconds. The newly forged elements decay, releasing radioactive heat that keeps the cloud glowing for days and weeks. For the first few days, the cloud shines mostly in blue and ultraviolet light. As it expands and cools, heavier elements take over the glow, and the cloud turns red. Astronomers have actually watched this color shift in real time, the way you might watch a campfire slowly fade from orange to ember to ash. The 2017 event was the breakthrough. After the gravitational wave detectors heard the merger, astronomers searched the sky for visible light. Within hours, a telescope in Chile picked up a faint new dot in a galaxy roughly 130 million light-years away. Over the next 2 weeks, more than 70 observatories on Earth and in space watched the dot brighten, then fade, then drift through colors. What they saw matched the predictions for a kilonova almost exactly. Spectra of the cloud showed clear chemical fingerprints of heavy elements being created. Estimates suggest that single collision produced about 10 times the mass of the Moon in gold and platinum. 10 moons of pure precious metal scattered into a galaxy where, eventually, some of it might fall into the cloud that builds a planet. It is humbling to think about. Every wedding band, every gold filling, every platinum spark plug, every layer of silver in a circuit board traces its ancestry back to events like this one. Not all from the same event, but all from collisions of objects so violent that nothing on the surface of Earth could survive even a glimpse. The same merger also taught astronomers something else. The flash of gamma rays that came with the kilonova proved that short gamma-ray bursts, mysterious cosmic flashes that had puzzled scientists for decades, are caused by neutron stars colliding. Two ancient mysteries solved by one event watched from a planet that did not exist when the original light started traveling. That 2017 event also did one more thing. It rang space and time like a bell, in a way that humans had only managed to detect for the first time a few years before. Imagine the surface of a still pond. Drop two heavy stones at the same time. Ripples spread out in circles. Now imagine those stones are not stones, but two dead stars circling each other. And the pond is not water, but the very fabric of space and time. The ripples in that fabric are gravitational waves. For decades, gravitational waves were a prediction, not an observation. Albert Einstein wrote them into his equations in 1916, but he himself doubted they would ever be measured. The waves are absurdly tiny. By the time they reach Earth from across the galaxy, they stretch and squish space by less than a fraction of the width of a proton. To detect that, humanity built one of the most sensitive instruments ever made. It is called LIGO. Two giant L-shaped tunnels, each arm 2.5 miles long, sit at opposite ends of the United States. Laser beams race down the arms, bounce off mirrors, and meet back at the center. If a gravitational wave passes through, one arm stretches slightly while the other squeezes. The difference is so small that engineers had to shield the experiment from passing trucks, distant earthquakes, ocean waves on the other side of the continent, and even the gentle pull of the moon on local rocks. In 2015, LIGO felt its first wave. It came from two black holes merging far, far away. The Nobel Prize followed 2 years later. But in 2017, LIGO felt something different. A signal that started softly and rose in pitch, like the chirp of a bird, for about 100 seconds before stopping. The black hole mergers it had detected before lasted barely a second. This one was longer, slower. The math said it had to be two objects smaller than black holes falling together in their final orbits. Two neutron stars. Within seconds, a gamma-ray satellite in space picked up a burst of gamma rays from exactly the same patch of sky. The two events were linked. The same event. Humans had, for the first time, heard a cosmic collision with both gravity and light. Telescopes raced to that patch of sky. They found the fading kilonova. They watched the glow shift through colors. They mapped the heavy elements being made. They confirmed in one swoop that gravitational waves are real, that neutron star mergers create kilonovas, that those mergers make the heavy elements in our bodies, and that short gamma ray bursts are caused by these collisions. 4 enormous physics mysteries, solved at once by one event from 130 million light-years away. The signal itself is something you can almost feel. Scientists have turned the gravitational wave data into sound, scaling it up into the human hearing range. It is a rising whistle, a long, fragile note that climbs in pitch as the two dead stars fall toward each other faster and faster. Then silence. The neutron stars have hit each other, and the universe has gone quiet again in that direction. For now. This is the moment astronomy entered a new era. Light alone is no longer the only way we see the cosmos. We can now feel its tremors. We can listen to the space-time around us. And one of the loudest songs we will ever hear in that language is the merger of two of the strangest objects nature ever cooked up. That same monstrous gravity, even from a single quiet neutron star, does something to light around it that defies what your eyes were built to see. Light, in everyday life, travels in straight lines. A laser pointer aimed at a wall makes a dot exactly where you expect. A flashlight cuts across a dark room in a clean beam. Your eyes work because photons leave an object, travel through space in straight paths, and land on your retina. Near a neutron star, none of that holds. Gravity, according to Einstein, is not a force tugging on things. It is a curve in the fabric of space and time. Where there is mass, that fabric dips. Light follows the curve. On Earth, the dip is so gentle that light goes essentially straight. Near a neutron star, the dip is steep enough to send light on long, looping arcs. Stand near a neutron star, looking outward, and the entire sky compresses. Stars behind you are pulled forward into your view, their light bent around the star and stretched toward your eyes. The sky is no longer a hemisphere above you. It becomes a small circle directly overhead, with the rest of your vision filled by the curved surface of the neutron star itself. Stand on the surface and the effect goes further. Light leaving the surface near your feet can curve around the star and reach you from the back. You see more of the star than half. In fact, depending on the exact mass, you might see something like 70% of the surface from any one viewpoint. It is as if the neutron star is gently peeking out from behind itself. Now look at the neutron star from a safe distance, say a few miles away. Instead of seeing a clean little sphere, you see a glowing ball with a halo of distorted images around it. Background stars, instead of being blocked by the neutron star's silhouette, smear into rings and arcs as their light wraps around the dense object. Astronomers call this gravitational lensing. We can actually see it happening when neutron stars or black holes pass in front of distant background stars in real telescope data. The effect changes the spectrum too. As light climbs out of the deep gravity well of a neutron star, it loses energy. Its wavelength stretches. Blue light becomes greener. Green light becomes yellower. Red light becomes infrared. The whole rainbow shifts toward the warm end as it escapes. This is called gravitational redshift, and it has been measured around white dwarfs and neutron stars alike. The result is that any conversation, any song, any signal sent from near a neutron star arrives at Earth slightly lower in pitch than it left. If a neutron star were close enough to see with the naked eye, and if you somehow survived its radiation, it would look like a small fierce dot of light surrounded by a faint halo of bent starlight. Background stars near it would appear to slide aside as it moved across the sky, like raindrops sliding down a glass. There is one more strange consequence of this gravity well. Time itself does not run the same way close to a neutron star as it does far away. A second on the surface of a neutron star is a little slower than a second on Earth, and while the difference might seem tiny, it is not. Over enough time, it would mean entire lifetimes drifting out of sync. Time in Einstein's universe is not a fixed thing. It bends, it stretches, it runs slower in the presence of strong gravity. Your wristwatch, sitting next to your bed, ticks ever so slightly slower than a clock on top of a tall mountain. The difference at the bottom of a building is something like a few microseconds per year compared to the top floor. Real, measurable, but invisible. Near a neutron star, that effect goes from invisible to dramatic. On the surface of a neutron star, time runs roughly 30% slower than it does in deep space. If you could stand there for what felt like 10 minutes, 14 minutes would have passed for a friend orbiting a few thousand miles overhead. Not a huge difference, but a meaningful one. After a single day on the surface, you would be more than 7 hours behind anyone watching from a safer distance. Imagine staying for a year. You return to your spaceship. By your own count, you have aged 12 months. Your crewmates would say you have been gone closer to 17. Letters from your family back on Earth would be slightly out of date by your reckoning, the people who wrote them having lived through more days than you have. Your favorite song would be a little older, and the world a little further down the line. Now extend that idea. If the neutron star were heavier, or if you could somehow stand closer to its center, the slowing would be more extreme. At the surface of the densest known neutron stars, time may run as much as 40% slower. Push closer to a black hole, and the effect grows toward infinity. There is no hard wall between neutron stars and black holes here. It is a sliding scale. A neutron star is gravity warping reality. A black hole is gravity warping reality so much that reality itself snaps shut around it. This is not science fiction. The same effect is real on Earth, in tiny amounts, every day. The GPS satellites that guide cars and phones have to constantly correct for it. Up in orbit, the satellites experience slightly weaker gravity than the surface of Earth, which means their clocks tick a little faster. Without correction, GPS positions would drift by miles within a day. The math that fixes that drift comes straight from the same equations that describe a neutron star's time field. There is something almost personal about all this. We tend to think of time as a strict referee, the one steady thing in a chaotic life. Time, the equalizer. Time, the metronome. Near a neutron star, time becomes another piece of geometry, something you can move through faster or slower depending on where you stand. It also raises the question of what time feels like to matter so dense that it almost touches the edge of becoming a black hole. To a thought experiment about a being living in a slowed reference frame, our entire civilization could rise and fall in the span of an afternoon. Empires and centuries and species glimpsed like a flicker. The neutron star itself feels none of this. It does not measure its own ticking against a faster clock. It simply spins and cools and quakes and broadcasts its pulses. Above its strange clock and crushing gravity just inches above the surface sits an even stranger feature, a layer of atmosphere so thin and so violent that no spaceship will ever pass through it intact. Earth's atmosphere is roughly 60 miles deep. The air gets thin around 12 miles up, where commercial planes cruise. Above that, you reach the layers of weather satellites, then the auroras, then finally the gentle handoff into space. A neutron star's atmosphere is about 4 inches thick. That is not a typo. The entire atmosphere of one of the most violent objects in nature is shorter than the length of your hand, and it sits smashed against the iron surface by the same gravity that crushes everything else into impossible densities. Inside that thin layer, the temperature is something like a few 100,000 degrees Fahrenheit. The atoms in it are mostly hydrogen with traces of helium and heavier elements, all stripped of their electrons and zipping around at a sizable fraction of the speed of light. The pressure is so enormous that the air, if you can call it air, is denser than the heaviest metals on Earth. A handful of it would weigh as much as a small mountain. This atmosphere, despite its thinness, is what we mostly see when we look at neutron stars with X-ray telescopes. The X-rays that escape into space have been filtered by these 4 inches of plasma. The shape of the spectrum, the way the light brightens and dims in certain colors, tells us about the composition of that layer. By studying that filter, scientists have been able to confirm the presence of certain elements on neutron star surfaces, including hints of iron and carbon. In some cases, the atmosphere is almost pure helium. In others, it is dominated by carbon. In a few cases, it has settled into layers, with heavier elements falling to the bottom and lighter ones floating above. Settled, in this case, taking about 1,000th of a second. The crushing gravity sorts the elements faster than you can think the words. Storms in this atmosphere do not look like Earth storms. There are no clouds, no rain, no wind in the way you would describe wind. Instead, magnetic fields drag charged particles into intense streams, like rivers of plasma along invisible rails. Where those streams hit the surface near the magnetic poles, they create burning hotspots, glowing slightly brighter than the rest of the star. As the star rotates, those hotspots sweep past our view and contribute to the pulses we detect. There is also a structure above the surface that we sometimes detect the way you might glimpse a glowing sea from the deck of a ship. Just above the 4-inch atmosphere, a thin shell of high-energy particles trapped in the star's magnetic field can sometimes generate light of its own. Imagine an electric storm fitted snugly around a city-sized object, lit by lightning that never stops. For a spacecraft to dip into that atmosphere is impossible. Long before any spacecraft could touch the upper edge of those 4 inches of plasma, the heat, the radiation, the gravity, and the magnetic field would have torn it into ions. Even our most advanced robotic probes, the ones that fly past Mercury and the Sun, would be unmade trying to get close. So we read this layer from a distance, like geologists studying a rock by the way it reflects sunlight. And what we read leads to something even more violent, because that thin shell does not always sit politely. Sometimes it shakes, and when it shakes, even a half a world away in our galaxy, our satellites feel it. Earthquakes can level cities. They release the kind of energy that makes the ground roll like ocean waves and topple buildings that took decades to design. The biggest earthquake ever recorded, in Chile in 1960, released roughly the same energy as 40,000 atomic bombs. A star quake on a neutron star releases more energy in 1/10 of a second than the sun has emitted in 100,000 years. The crust of a neutron star is the thinnest, hardest, weirdest shell in the universe. It is only a few hundred yards thick, layered with nuclear pasta, locked tight by the strongest material we know of. Above it sits the magnetic field. Below it sits the superfluid sea of free neutrons. The crust is the membrane between two violent worlds. That membrane is under constant stress. The magnetic field shifts, the spinning slows, the superfluid below sloshes. Bits of the crust get tugged by all of these forces at once. Eventually, somewhere along its perfectly hard, perfectly brittle surface, the stress wins. The crust cracks. When a city-sized crust cracks, the effects are felt across the galaxy. In December of 2004, an instrument in orbit recorded a flash of gamma rays so bright that it briefly outshone the full moon. The signal came from a magnetar called SGR 180620, roughly 50,000 light-years away, on the far side of the Milky Way. In 1/5 of a second, that single neutron star released more energy than the Sun would in the next 250,000 years. The reason was a starquake. The crust of that magnetar had cracked, the magnetic field had snapped into a new shape, and an unimaginable wave of energy had been released into space. Earth, 50,000 light-years away, sat behind a thick fog of dust and gas, and still our atmosphere was disturbed enough to detect the event. Some satellites were briefly blinded. The pulse compressed our upper atmosphere inward by about 1/10, the kind of pressure normally only delivered by a powerful solar storm. If that same event had happened from within roughly 10 light-years of us, scientists believe the radiation would have stripped a major portion of our ozone layer. The food chain would have collapsed within months. Most surface life would not have survived a year. Theories link similar bursts to certain mass extinctions in Earth's deep past, though those links remain unproven. The starquake itself, on the magnetar, would have looked tiny if you could somehow see it. The crust might have shifted by less than half an inch in places. But the shift was in something 10 billion times stronger than steel, in a field 1 quadrillion times stronger than Earth's magnetism, on a body more massive than the Sun. A nudge in those conditions is a thunderbolt. Smaller starquakes happen all the time on younger neutron stars. They contribute to those mysterious glitches in pulsar timing. Larger ones rearrange the magnetic field and produce X-ray flares that flicker across our detectors for weeks afterward. The ground we live on, with its mild and patient earthquakes, is nothing compared to the brittle armor of a dead star. And of all the neutron stars in our sky, one sits closer to us than the rest, a solitary cinder drifting in our cosmic neighborhood that astronomers can study almost in detail. Roughly 400 light-years from Earth, in the southern constellation Corona Australis, sits a small, lonely cinder. Its catalogue name is RxJone 8565-3754. Astronomers nicknamed it the closest known neutron star. In the language of the cosmos, 400 light-years is practically next door. Our galaxy is about 100,000 light-years across. The nearest known black hole is roughly 1,000 light-years away. Yet, RxJ 1856 sits closer to us than most of the stars you can see on a clear night. It has no companion, no accretion disk, no bright flares. It just drifts, slowly cooling, glowing softly in X-rays, at a surface temperature of about 1,000,000 degrees Fahrenheit. Its mass is roughly that of the Sun, packed into a sphere only about 12 miles wide. We have measured its motion across the sky. We have measured its temperature. We have measured the slight wobble in its position caused by the distortion of space around it. This is the cleanest, calmest neutron star we have ever found, and it has been a quiet headache for theorists. The trouble is its size. Most measurements suggest RxJ 1856 is slightly smaller than a typical neutron star of its mass should be. By the equations we use for ordinary neutron star material, an object that heavy ought to be a few hundred yards larger across. The deficit is small but consistent. A handful of physicists have wondered if this is the fingerprint of a quark star. If the very core of RxJ 1856 has dissolved into free quarks, it would shrink the entire object by exactly the kind of amount we seem to be measuring. So far, the data is not strong enough to confirm or rule out the idea. The neighbor next door may turn out to be one of the strangest objects we have ever found, or it may be perfectly normal once we sharpen our instruments. What we can say with confidence is that it is moving. RxJ 1856 is heading roughly toward the constellation Capricornus at about 10,000 miles per second relative to Earth. Imagine the speeds of our fastest spacecraft. New Horizons, which flew past Pluto, traveled at about 10 miles per second. RxJ1856 is moving 1,000 times faster, yet at that speed, at that distance, it is in no danger of approaching us in any meaningful way during the lifetime of our solar system. It will not pass through Earth's neighborhood for millions of years, if ever. But the math allows for one disturbing thought experiment. If a neutron star like RxJ1856 ever did pass through the outer reaches of our solar system, the consequences would be catastrophic. It would not need to hit Earth to ruin us. Its gravity alone, brushing past the orbit of Neptune, would yank the planets into chaos. Orbits would warp. Some planets might be flung out of the solar system entirely. Others might fall toward the Sun. Earth's path around the Sun could become so warped that we would freeze or fry, depending on which direction the new orbit carried us. The good news is that no such close encounter is currently predicted. The bad news is that one almost certainly happened, somewhere in the deep past of our galaxy, to other worlds. Imagine, just for a thought experiment, that a neutron star is on a collision course with the outer edge of our solar system. Not a direct hit, just a flyby, at the distance of the outer planets. Astronomers spot it 10 years ahead of time. Civilization knows it is coming. The countdown begins. Year 1. The neutron star is still far beyond Pluto. Its mass and motion are tracked by telescopes worldwide. Models predict it will pass through the Kuiper Belt, the region of icy bodies that surrounds the outer solar system. Mathematicians refine their calculations. Year 3. The neutron star's gravity has begun to disturb the orbits of distant comets. Long-period comets that should have stayed quietly drifting in the outer dark are pulled into new paths. Some will fall toward the inner solar system over the coming decades. A few will eventually hit planets, including Earth. Year 5. Through powerful telescopes, the neutron star appears as a faint pinprick of strange light, surrounded by a halo of bent starlight, distorting the constellations around it like a thumb pressed into still water. Optical scientists watch in awe as the patterns of background stars near it shimmer and shift. Year 7. As the neutron star enters the realm of the gas giants, the orbits of Neptune and Uranus begin to wobble. The orbital periods change. The seasons of those distant worlds, if they have anything you could call seasons, are reshuffled. Probes from Earth, sent decades earlier, lose contact as their predicted positions no longer match reality. Year 9. The neutron star sweeps past Saturn's orbit. Saturn itself is not hit, but its rings, fragile and delicate, are disturbed by the passing gravity. Some material is yanked away. New comets are flung in toward the Sun. Jupiter, the heaviest planet in our system, is jostled in its orbit. Year 10, the neutron star reaches its closest approach. It does not touch Earth. It passes through a region between Mars and Jupiter, but its gravity is now strong enough to tug on every planet. Earth's orbit warps. The familiar 12-month year stretches or shrinks. The moon's path around Earth twists. Tides, normally a few feet high, become hundreds of feet high. Coastlines drown under impossible tides. The radiation from the neutron star, even at this distance, would bathe Earth's upper atmosphere in damaging X-rays. The ozone layer would thin. Some life on the surface would survive, hidden in the oceans and underground, but most of the surface ecosystem would collapse within weeks. Then the neutron star moves on. It pulls away from the Sun on its arc, through the galaxy, leaving us bruised. Earth's orbit, even after the visitor has gone, will not snap back to its original shape. The new path may be more elliptical. Our average distance to the Sun could shift. Our climate could change forever. In some scenarios, the gravity is so disruptive that Earth is flung out of the solar system entirely, frozen, dark, hurtling alone through interstellar space at thousands of miles per second. This is not a prediction. No such neutron star is currently aimed at us. But the thought experiment shows how thoroughly one of these objects could rewrite a solar system. The simple presence of a neutron star in a neighborhood is enough to break things. And sometimes, far away in the galaxy, Neutron stars send out blasts of energy so brief and so bright that astronomers have spent decades trying to figure out where they come from. In 2007, astronomers were sifting through old data from a radio telescope in Australia. Buried in the recordings from 6 years earlier, they found something strange. A signal lasting roughly 5 milliseconds, 5,000ths of a second, bright enough to outshine almost everything else in the radio sky for that instant. Then gone. By the time they searched for more, the signal had vanished forever. That brief pulse turned out to be the first known fast radio burst. Since then, astronomers have detected thousands more. They come from random directions in the sky. Most last only a few milliseconds. Some are one-time events. Others repeat from the same source, sometimes flickering thousands of times over the course of months. The energy in one of these bursts is staggering. A typical fast radio burst releases as much energy in those few milliseconds as the sun emits in 3 full days. Some release more energy than the sun puts out in a year, all packed into a flash too brief to even see. For more than a decade, the source of these bursts was a complete mystery. Theories ranged from colliding neutron stars to evaporating black holes to, in some headlines, alien signals. Then, in 2020, the question cracked open. A burst came from inside our own galaxy. Astronomers traced it to a magnetar, the same kind of object we visited earlier, with magnetic fields a quadrillion times stronger than Earth's. The magnetar, called SGR 1935 plus 2154, sat about 30,000 light-years from us. It briefly flared with a burst that matched the energy and signature of the distant fast radio bursts almost exactly. For the first time, scientists had a confirmed source. Many fast radio bursts, perhaps most of them, appear to come from magnetars. The brief flashes are likely produced when those nightmarish magnetic fields suddenly reconfigure, releasing energy in coherent bursts of radio waves that race across billions of light-years of space. But the picture is not complete. Some fast radio bursts have been linked to environments where magnetars do not seem to fit. A few come from old, calm regions of space far from any known star-forming activity. Others repeat in patterns too steady to match the chaotic behavior of magnetars. There may be more than one cause. There may be entire categories of fast radio burst we have not yet sorted out. There is also the question of what makes the bursts so bright. To shine across the universe with the power of 3 days of sunlight in a few milliseconds, the emission has to be coherent. That means the radio waves are emitted in perfect synchrony, like a laser, rather than scattered randomly like a campfire. Producing coherent radio emission of that intensity is not easy. It requires conditions that even the most extreme magnetars push to the edge. Each fast radio burst is a postcard from one of those edges, a note from a dead star tearing itself apart for an instant before settling back into the quiet of its rotation. In the time it takes you to blink, that single flash has carried more energy than your entire civilization will use in centuries. These flashes also help us measure the universe itself, because they pass through so much intergalactic gas on their way to us. The way they arrive at different wavelengths reveals the density of matter between galaxies. They are not just curiosities, they are tools for mapping the cosmos. About 6,500 light-years from Earth, in the constellation Taurus, sits a glowing cloud of gas called the Crab Nebula. It looks, through a small telescope, like a soft smudge of light. Through a powerful one, it resolves into a tangle of filaments, wisps and shells, expanding outward at over 1,000 miles per second. The Crab Nebula is the wreckage of a supernova that exploded in the year 1054. Chinese astronomers recorded the event. They described a guest star, visible during the day for over 3 weeks, and visible at night for nearly 2 years. 970 years later, the debris from that explosion is still spreading, still glowing, still cooling. At the very center of the cloud sits a neutron star, the Crab Pulsar. It is one of the youngest, most active neutron stars we know of, and one of the best studied in all of astronomy. The Crab pulsar spins 30 times every second. With each spin, it sweeps a pair of bright beams across space. Like the lighthouse we mentioned earlier, Earth happens to lie in the path of those beams, so we receive a flash from the Crab 30 times a second across nearly every wavelength of light, from radio waves up to gamma rays. It is, in many ways, the model neutron star. When astronomers want to understand how pulsars work, they often start by looking at the Crab. It is bright enough, close enough, and young enough that we can see fine details of how it loses energy, how it shapes the gas cloud around it, and how its beams change over time. The Crab pulsar is also a power plant. Its energy output in radiation and high-speed particles is around 100,000 times that of our Sun. Almost all of it pours into the gas cloud around the neutron star, lighting up the Crab nebula from the inside. The eerie blue glow at the center of the Crab is mostly that radiation, exciting the surrounding gas like a stage spotlight from behind a curtain. That power has to come from somewhere. It comes from the spin. As the Crab pulsar emits radiation, it loses rotational energy. Each year, its rotation slows by a measurable fraction. The pulses arrive slightly later. Astronomers have been watching that slowdown for decades. The neutron star is bleeding its spin into light and particles, slowly converting motion into glow. At its current rate, the Crab pulsar will continue producing high-energy radiation for tens of thousands more years, gradually fading. Long before it stops, the gas cloud around it will spread thin and dissolve into the surrounding galaxy. The neutron star will then drift alone, a much quieter cinder, slowly cooling. The Crab also offered one of the first proofs that pulsars are actually neutron stars. When astronomers first found pulsars, the question was wide open. Could they be white dwarfs, the dense corpses of normal stars? Could they be something else entirely? But white dwarfs cannot spin 30 times a second without flying apart. Only a neutron star, with its insane density and tiny size, could rotate that quickly and survive. The Crab settled the debate. Some neutron stars do not live alone in their nebulae. Some have a partner star nearby, and that partner pays a very heavy price for the company. In a binary system, two stars orbit each other. Sometimes one of those stars dies first, becoming a neutron star, while the other continues to live as an ordinary star. The neutron star is small, only about 12 miles wide. The ordinary star may be enormous. They orbit each other in silence for millions of years. Then, slowly, the dance turns predatory. If the two stars are close enough, the neutron star's gravity begins to draw matter off the surface of its companion. Hydrogen and helium peel away from the larger star and form a glowing disk around the neutron star. We call this disk an accretion disk. It glows in X-rays as the falling matter heats up to millions of degrees on its way down. Up close, the disk looks like a giant flat ribbon of glowing gas swirling around the neutron star like water down a drain. The inner edge of the disk almost touches the surface of the neutron star itself. As the gas spirals inward, it speeds up, it heats up. By the time it lands on the surface, it has fallen at nearly half the speed of light. The impact is staggering. Each falling atom adds energy to the surface. The neutron star glows hotter. X-rays pour out into space. From Earth, we can see those X-rays and we can use their pattern to study what is happening on the surface. Sometimes the matter does not just land softly, it builds up over time. The hydrogen layer thickens, gets denser, gets hotter. Eventually, deep in the layer, the temperature passes a threshold and the entire layer explodes in a runaway nuclear fusion reaction. We see a sudden flash of X-rays from that part of the sky, then a slow fade as the surface settles back down. These are called X-ray bursts. Some neutron stars in binary systems have X-ray bursts every few hours, year after year, like a slow drumbeat measured from across the galaxy. The companion star, meanwhile, is dying. Its outer layers are being stripped away, peeled off in long streamers that arc toward the neutron star. The companion's mass shrinks. Its color and brightness change. Some companions get whittled down to husks, only a small fraction of their original mass remaining. Some companions are completely consumed. There is a particularly sinister category of these systems called black widow pulsars. In these, a fast-spinning neutron star sits beside a tiny companion star that it is actively eating with its radiation. The neutron star's energetic particles strip the companion's surface, blasting away gas day after day. Eventually, the companion is reduced to almost nothing, leaving the neutron star alone in space with a faint trail of plasma. There is also a related class called redback pulsars, where the companion is slightly larger and not yet fully consumed. These systems show us snapshots of stars in different stages of being eaten. It is, in cosmic terms, a slow horror movie. One star dies, becomes incredibly dense, and then patiently feeds on its surviving partner over millions of years. Each meal makes the predator spin faster. Each meal weakens the prey, and as the gas falls onto the neutron star, it does not always land gently. Sometimes the layers explode in such precise, energetic ways that the entire star briefly flares like a beacon. When fresh hydrogen lands on the surface of a neutron star in a binary system, it does not stay hydrogen for long. The crushing gravity squeezes it. The heat from the falling matter cooks it. In a matter of hours or days, the new layer of hydrogen fuses into helium. Then helium piles up below, getting hotter and hotter as more material falls on top. Eventually, somewhere in that buried helium layer, the conditions for runaway fusion are reached. The entire layer ignites in a flash. In a few seconds, an enormous amount of helium is converted into heavier elements. The energy released is so intense that it surges through the surface and out into space as a burst of X-rays. From Earth, we see this as a sudden spike in X-ray intensity from a known binary system. The signal climbs in less than a second, then fades over the next few minutes. We call these events Type 1 X-ray bursts. Some neutron stars have them every few hours, some only every few days. They are the most reliable nuclear explosions in the universe, and they happen so often in our galaxy that satellites catch them on a near-daily basis. The energy in one burst is staggering. A single Type 1 X-ray burst releases more energy in a few seconds than the Sun does in 2 weeks. Now imagine that energy concentrated on a sphere only 12 miles across. The surface of the neutron star briefly becomes one of the hottest objects in the universe outside of supernovae themselves. There is a stranger cousin to these bursts. Sometimes, the layer that ignites is not just helium, but a deeper layer of carbon. Carbon takes much longer to build up. When it finally ignites, the result is a superburst. A superburst lasts not seconds, but hours. The energy released can be 1,000 times that of a normal X-ray burst. We have only seen a few dozen of these in total, scattered across decades of observation. Each burst leaves a small fingerprint on the neutron star. The newly forged heavier elements get mixed into the surface. The crust gets a small jolt. The atmosphere, all 4 inches of it, briefly puffs up before settling again. This is matter being recycled in real time. Hydrogen falls, becomes helium, becomes carbon, becomes iron, becomes part of the crust. Over millions of years, an old neutron star in an active binary system can build up enough material on its surface to actually grow heavier. The neutron star adds mass, slowly. Its surface composition changes. The accretion disk above it brightens or dims as the companion offers more or less material. There is also a critical limit hidden in all of this. If a neutron star keeps gaining mass, eventually it will pass a threshold beyond which neutrons can no longer hold themselves up. The maximum mass a neutron star can have is somewhere around 2.25 to 2.5 times the mass of the Sun. Push past that line, and even nuclear pasta cannot save it. When a neutron star crosses that line, the result is not another, slightly bigger neutron star. The result is a black hole. The exact moment when matter transitions from neutron star to black hole is one of the most poorly understood events in physics. Right at that edge, the universe has not yet shown us its full hand. Every neutron star sits on a knife's edge. Its gravity wants to pull it inward. Its neutron degeneracy pressure pushes back. The two forces balance, and the star holds together. The balance is fragile. If a neutron star gets heavy enough, the balance breaks. There is a number that astronomers and physicists have been chasing for decades. It is called the Tolman-Oppenheimer-Volkoff limit, after the three scientists who first calculated it in the late 1930s. The limit is the maximum mass a neutron star can have before its own gravity overwhelms its support pressure. Best current estimates place it somewhere between roughly 2.25 and 2.5 times the mass of the Sun. Above that, no known force can keep the star from collapsing. What happens next is not a slow event. There is no fade. There is no gentle settling. In a fraction of a second, the neutron star folds in on itself. The crust falls. The pasta layers fall. The sea of neutrons falls. The core, possibly a quark soup, falls. The whole sphere shrinks until its surface dips below a specific size called the event horizon. Once that horizon forms, no light can escape from inside. The neutron star is gone. In its place is a stellar mass black hole, about 3 to 5 times the mass of the Sun, with an event horizon only a few miles across. We have actually seen evidence of this transition. In some neutron star mergers, the combined mass of the two stars is too high for a stable neutron star to form. The merger product is a neutron star for only a few milliseconds before collapsing into a black hole. The gravitational wave signal from these events drops off slightly differently than from a long-lived neutron star. By comparing the signals, scientists have been able to refine where the actual mass limit sits. There is something poetic about this line. Below it, you have an object made of the strangest matter in the universe, with a visible surface, a magnetic field, an atmosphere, and a thermal glow. Above it, you have a region of space from which not even light can escape. Two completely different physical objects, separated by less than a quarter of a solar mass. A whisker of difference in the cosmic ledger. That whisker has consequences. A neutron star can be studied. We can measure its size, temperature, spin, magnetism, and chemical composition. A black hole shows us none of those things. From the outside, a black hole is described by only 3 numbers: mass, spin, and electric charge. Everything else about whatever fell in is hidden behind the event horizon, possibly forever. This means a neutron star is rich in information. A black hole is barren. The crossing of that line is, in a sense, the moment when the universe stops telling us a story about a specific object and starts only telling us its weight. It also raises a question that physicists love. Is there an intermediate state between a neutron star and a black hole, where the gravity is too strong for normal neutron matter, but not yet strong enough to form a horizon? Some have proposed quark stars or strange stars as candidates for that middle ground. So far, the data does not let us say for sure. What we can say is that the dividing line is real, and it is sharp, and it is sometimes crossed in real time. Astronomers have a name for the strange region around 2 solar masses, where heavy neutron stars and light black holes might both exist. They call it the mass gap. For decades, observations suggested that black holes formed from collapsed stars start at about 5 solar masses, and neutron stars top out around 2. Between those two numbers, there was a curious silence. Almost no objects had been detected with masses between about 2 and 5 times the Sun. Was this gap real? Or was it just a quirk of how we look for these objects? In the past few years, gravitational wave detectors have started filling in the gap. In 2020, astronomers reported a merger that included an object of roughly 2.5 solar masses. They could not tell, from the data alone, whether it was the heaviest known neutron star or the lightest known black hole. The signal was consistent with either. The mystery deepened. A heavy neutron star is a strange thing on its own. The closer you push a neutron star to the mass limit, the more its inside reshapes itself. The pressures at its core may be high enough to produce quark matter. Its size may shrink. Its quakes may change in frequency. Its surface may grow brighter or dimmer in ways we do not fully understand. A very light black hole is just as strange. Most stellar mass black holes form when a star much more massive than the Sun collapses, leaving behind several solar masses. To form a black hole as light as 3 solar masses, the original star must have been right at the edge of the right conditions. The collapse must have been just powerful enough to crush its core past the neutron limit, but not so powerful that the remnant was much bigger. Some of these light black holes may form from neutron star mergers. When 2 neutron stars combine, the result is often a single, more massive object. If their combined mass crosses the limit, the new object collapses straight into a black hole. The line between a heavy neutron star and a light black hole then becomes a question of which side of the mass limit the merger landed on. For us standing on Earth, the difference between these two cases is huge. A heavy neutron star can be studied for years. We can detect its rotation, its magnetic field, the X-rays from its surface. A light black hole shows us nothing once it forms. The transition between being a neutron star with a visible surface and being a black hole with only a hidden interior takes less than a heartbeat. The mass gap is also important because it helps us understand how stars die. The fact that there were so few detections in this range suggested for years that some special process pushes dying cores either down into low-mass neutron stars or up into higher-mass black holes, with little in between. As we fill in the gap with new detections, we will refine the rules of stellar death. What is certain is that the universe is full of these edge cases. Out there in the dark, somewhere right now, an old neutron star is sitting at 1.5 solar masses. Another is teetering near 2.5. A black hole formed from a merger is sitting just above the line. Each of them is a different chapter in the same story. We have also found neutron stars that started slow and ended very fast, fed by their neighbors for billions of years. In a binary system, a neutron star can do more than just steal matter. Over time, it can be spun up to extraordinary speeds. We touched on this earlier when we talked about millisecond pulsars. Now we will look at the long process behind it. An ordinary isolated pulsar slows down. Each rotation loses a sliver of energy as radiation. After 10 million years, the neutron star is rotating only a few times per second. After 100 million years, it might rotate once every few seconds. After 1 billion years, it has slowed so much that it can no longer produce detectable pulses. It crosses what astronomers call the death line and goes dark. But place that aging neutron star in a binary system with a still living companion, and the story changes. As the neutron star starts to draw matter off its companion, that matter falls onto the neutron star in a long, gentle stream. The matter has angular momentum. It is moving in a circle. When it lands on the surface, it transfers a little bit of its rotational push to the star. Imagine a heavy top slowly winding down. Now imagine that you start spinning it again, very gradually, with the gentlest of touches. Over thousands of years, the touches add up. The top spins faster. Over millions of years, the rotation rate climbs into the hundreds of times per second. These resurrected pulsars are called recycled pulsars. They are old, they are no longer young, hot, or magnetically violent. Their magnetic fields have decayed to a fraction of what they once were, but they spin at speeds that young pulsars cannot reach because they have been fed for millions of years by a partner. The fastest known pulsars, the millisecond ones we discussed earlier, are almost all recycled. They live in binary systems, often with the ghost of a companion star still in orbit. Some of those companions are stripped down to almost nothing. Some have evaporated completely. There is a subtle and beautiful piece of irony here. The youngest, freshest neutron stars are the ones with the strongest magnetic fields, the most violent quakes, and the most chaotic behavior. The oldest neutron stars, by contrast, can be the steadiest clocks. As the magnetic field decays over time, the neutron star's rotation becomes more and more predictable. Millisecond pulsars are so steady that some of them rival the best atomic clocks on Earth for precision over years. This combination of speed and steadiness makes recycled pulsars uniquely useful. Because their pulses arrive with such regular timing, any tiny disturbance in their arrival times becomes detectable. Astronomers can use them as cosmic detectors of all kinds of phenomena, from the orbits of their own planetary companions to the gentle stretching of space itself. Yes, planetary companions. Some recycled pulsars actually have planets orbiting them. The first planets ever discovered outside our solar system, found in 1992, were orbiting a millisecond pulsar called PSR B1257+12. These worlds, often called pulsar planets, are bathed in deadly radiation and unlikely to support any life we recognize. But their existence proved that planets could form even around the strangest stars. So an old neutron star, after being eaten by its partner and reborn at fantastic spin speeds, can also be a host to a small system of dead worlds. The galaxy is stranger than it has any right to be. If you watch a single pulsar carefully enough, you can detect when its pulses arrive at Earth, down to less than a microsecond. Watch dozens of pulsars across the sky at once, and you have a network of cosmic clocks. Any disturbance that affects them all in a particular pattern can be teased out from the data. This is the idea behind a pulsar timing array. For decades, scientists have been monitoring sets of millisecond pulsars spread across the sky. Each pulsar acts as a metronome, and the array as a whole acts as a giant detector for tiny effects. The most exciting target of this work has been a kind of gravitational wave that ground-based instruments like LIGO cannot catch. LIGO detects high-pitched gravitational waves from neutron star and black hole mergers, where the whole event lasts seconds. But the universe also hums with much lower-pitched gravitational waves, with frequencies so slow that the wave takes years to oscillate. These low waves come from objects like supermassive black hole binaries, the kind that live at the centers of galaxies and slowly spiral toward each other over millions of years. To detect these slow waves, you cannot use a 2-mile-long detector on Earth. You need a much bigger one. A pulsar timing array effectively turns the entire galaxy into a detector. The distance from Earth to each pulsar is thousands of light years. A passing gravitational wave gently stretches and squeezes those distances. The result is a tiny, correlated shift in the timing of pulses arriving from many pulsars at once. In June of 2023, multiple international collaborations announced that they had detected the first evidence of this gravitational wave background, the hum of the universe, as it were, a constant rumble of low-pitched gravitational waves, almost certainly produced by countless pairs of supermassive black holes, slowly spiraling together in galaxies all across the cosmos. Think about what that means. By watching the steady tick of dead stars across our galaxy, we measured the chorus of black holes from billions of light years away. The data has been growing stronger ever since, with more pulsars added and longer observation times refining the signal. This is one of the wildest and most beautiful uses of neutron stars. We use them as ancient clocks. We use them as gravitational wave detectors. We use them as natural laboratories for nuclear physics. They serve us in ways that no engineered instrument ever could, simply by being themselves, ticking faithfully across the dark. A more practical use is also on the horizon, because each pulsar has a unique signature, a unique pulse pattern, a unique location in space. Scientists have proposed using a small set of millisecond pulsars as a kind of cosmic positioning system for interstellar travel. A spacecraft far from Earth, beyond the range of any GPS satellite, could use the pulses from a handful of well-known pulsars to figure out exactly where it is in the galaxy to within a few miles. NASA has already tested a prototype of this idea on the International Space Station. The instrument is called the Station Explorer for X-ray timing and navigation technology. It successfully used pulsar pulses to determine the station's position in orbit to within a few miles. Tiny by Earth standards, but a proof of concept for navigating across the galaxy. When humans finally send probes beyond the solar system, they may find their way home not by stars they can see, but by ticking lighthouses from long-dead suns. Imagine, for a thought experiment, a planet orbiting a neutron star. Could any kind of life take hold there? The first problem is the radiation. A typical neutron star floods its surroundings with X-rays. A magnetar floods them with gamma rays as well. Anywhere close enough to feel warmth from the surface of the star is also drenched in radiation that would shred molecules and sterilize surfaces. So a planet orbiting close enough to get warmth gets killed by the energy that warms it. The second problem is the orbit. A neutron star is so small and so dense that the habitable distance, if there is one, is much closer than you would think. A planet orbiting at the right temperature might be only a few million miles away from the surface, screaming around its star in a matter of days. Its year, if you could call it that, might be hours long. The third problem is the magnetic field. Even far from the surface, a strong magnetic field can disrupt biochemistry. Cells that depend on delicate ion gradients to function might find their internal machinery interrupted by even modest magnetic interference. Life as we know it would struggle. Now suppose, instead of life on the surface, you imagine life deep inside the neutron star itself. Could there be exotic life in the nuclear pasta? In the sea of free neutrons? In the quark soup, if there is one? This is genuinely speculative. A few physicists have played with the idea of nuclear life, organisms made not of atoms, but of nucleons, exchanging energy through the strong nuclear force rather than chemistry. In such a world, processes would happen on timescales billions of times faster than chemistry. A whole civilization could rise and fall in the time it takes you to read this paragraph. Other physicists have wondered about life in the magnetic field itself. Patterns of plasma, twisted by magnetic forces, might in principle form stable structures that pass information, grow, and reproduce. Whether anything like that has ever happened is unknown. There is also the question of artificial life. If a civilization ever reached the technical level required to build structures around a neutron star, the energy available would be staggering. The radiation alone, harnessed by a swarm of solar collectors, could power a galaxy-spanning culture. Some theorists have proposed that highly advanced civilizations might choose to harvest energy from spinning neutron stars by extracting their rotational energy directly, like winding down a top to power a city. We have no evidence that any such structures exist, but the energy budget is real. The neutron stars are real. The future may bring its own surprises. For the ordinary life that we know, the kind made of carbon and water and warm sunlight, a neutron star is essentially the worst possible neighbor. Too hot, too cold, too magnetic, too radioactive, too violent. The only way to enjoy one is from a safe distance, with sensitive instruments, on a planet far away. Earth, fortunately, is exactly such a place. We are far enough from the nearest neutron star to be untouched by its radiation. We are close enough to watch them with our telescopes. We are alive at a time when humans can read pulsars, listen to their gravitational hum, and watch their distant collisions in real time. We are spectators with the best seats in the house, and we did not even have to build the show. In 1972 and 1973, two spacecraft named Pioneer 10 and Pioneer 11 launched from Earth, bound for the outer solar system. Both of them carried, attached to their hulls, a small plaque designed by a team led by astronomer Carl Sagan. The plaque was meant to identify Earth to any alien civilization that might one day intercept the spacecraft. The plaque included a man, a woman, and the solar system. It also included a map. The map was not made of stars. It was made of pulsars. 14 lines radiated outward from a central dot representing our Sun. Each line ended at a known pulsar, with a precise pulse rate marked along its length in binary code. The idea was that any sufficiently advanced civilization in the galaxy could identify those pulsars by their unique pulse rates, triangulate their positions, and pinpoint exactly where the Sun is in space, even hundreds of millions of years from now. It was the most ambitious return address ever written. This map worked because pulsars are unique. Each one has its own pulse rate, slightly different from every other pulsar in the galaxy. The pulse rate is also predictable, slowing down by a known, slow amount over time. So a civilization decoding the plaque could account for the slowdown, run the math backward, and figure out which pulsar matched which line, even if the message took millions of years to arrive. Pioneer 10 and Pioneer 11 are still out there, traveling silently. We lost contact with them years ago, but the plaques are still attached. The map is still readable. The neutron stars it points to are still spinning. If, billions of years from now, some passing intelligence finds one of those spacecraft, it could still use the pulsar map to find a small yellow star in a galaxy that may not even look the same anymore. That same idea has been refined over the decades. The Voyager spacecraft carries similar maps, drawn with even more pulsars. Newer probe designs continue the tradition. Every craft leaving the solar system carries the rhythm of dead stars as part of its identity. There is something deeply moving about this. Humans, alive for a flicker of cosmic time, on a small planet orbiting an unremarkable star, chose to mark their position in the galaxy using objects that are some of the oldest, most stable beacons we know. Pulsars formed long before our planet existed, and they will continue to tick long after our civilization is gone. By tying our location to theirs, we made our address something the galaxy itself could read. There is also a hint of irony in it. Pulsars cannot last forever. Even the steadiest of them slows down, fades, and eventually goes dark. But that fading happens over billions of years. On any timescale that matters to a civilization, or even a species, the map will remain readable. There are people who joke that this is the longest-lasting message humanity has ever written. The flag on the moon will fade, cities will fall, languages will vanish, even continents will shift on a long enough timescale. But the pulsar map, carried on small metal plaques out into the dark, points to where we lived, with the help of dead stars that will keep ticking long after the last human heartbeat. The universe holds even deeper riddles in those ticking hearts. Some of them, even today, remain unsolved. Step back inside a neutron star for a final descent, past the 4-inch atmosphere, past the layers of nuclear pasta, past the sea of free neutrons. You are now at the very center, the deepest part of the densest object in nature. What is here? The honest answer is that we do not know. The center of a neutron star is the most uncertain region of physics that humans currently study. The pressure there is roughly 10 times higher than anywhere else inside the star. The density is several times that of an atomic nucleus. Conditions are so extreme that none of our laboratory experiments can reproduce them, even for an instant. There are several theories about what kind of matter fills the core. One theory says the core is still a sea of neutrons, just at a higher density. This is the simplest case. The neutrons remain neutrons, packed tighter and tighter, with the strong nuclear force holding them in line. Another theory says the core dissolves into a quark soup. The neutrons lose their boundaries. Their quarks float freely, forming a kind of matter that exists nowhere else in the universe, except possibly in the early moments after the Big Bang. We met this in an earlier chapter. A third theory says the core contains hyperons. Hyperons are a kind of heavy cousin of the neutron, with one of the quarks replaced by a heavier kind called a strange quark. Hyperons exist in particle accelerators on Earth, but only for tiny fractions of a second before decaying. Under the conditions inside a neutron star core, they might exist as stable, long-lived matter. A fourth theory says the core is filled with a different kind of quark matter, made of equal parts of 3 quark flavors. This is the strange matter idea we touched on earlier. If true, the very stuff of the core would be the most stable form of matter in nature, more stable than the iron in your blood. There are also theories involving exotic particle condensates, hypothetical objects with no Earth analog at all. We may be able to distinguish between these theories with future observations. The exact size and shape of a neutron star depends on what is in its core. By measuring the radii of neutron stars more precisely, especially the ones whose masses we already know, scientists can rule some theories in or out. NASA's NICER instrument, attached to the International Space Station, has been doing exactly that. By timing pulses from specific neutron stars in detail, it has produced the most accurate maps of neutron star sizes ever made. So far, the data is helping. It is also leaving plenty of room for surprises. Some neutron stars seem slightly bigger than the simplest theories would suggest, others slightly smaller. Each new measurement nudges the picture, but no single theory has yet been confirmed. This is one of the most active frontiers in physics today. The answer matters not only because we want to understand neutron stars. It matters because the same physics governs what happens inside black holes, inside the cores of supernovae, and inside the moments after the Big Bang. The core of a neutron star is in a real sense a glimpse into the earliest universe and the deepest gravity wells of the cosmos. We are squinting through a tiny window into one of nature's last secrets, and we are, slowly, starting to see. A neutron star lives an extraordinary life. It is born in fire, glows hotter than any laboratory could ever create, spins faster than any human-made object, and reshapes the matter in its core into forms we cannot reproduce. It can outshine its own galaxy, sing across the universe in gravitational waves, and forge the gold in our jewelry. But it does not last forever. Over hundreds of millions of years, a neutron star loses energy. Its rotation slows, its magnetic field decays, its surface cools, slowly, by a few degrees per year. The pulses get weaker, the radio emission fades. Eventually, the neutron star crosses the death line and stops being a pulsar at all. It becomes a quiet, drifting object, still incredibly dense, still spinning slowly, but no longer broadcasting. That phase can last billions of years. The neutron star coasts through the galaxy, gradually cooling. Its surface temperature drops from millions of degrees to thousands, then to hundreds. After tens of billions of years, longer than the current age of the universe, the surface temperature would finally drop to something that does not glow brightly in any wavelength we usually observe. Even then, the neutron star is not truly dead. It is still made of the same impossibly dense matter. It still has gravity that could rip apart any spacecraft. It still has a magnetic field, weaker but real, surrounding it. It is more like a cooled cinder than a true grave. If left alone in deep space, a neutron star can persist for an unimaginably long time. Some calculations suggest neutron stars can last for trillions of years, far outliving the current universe. They are among the longest-lived objects in any reasonable cosmological scenario. Some theories propose that, over absurdly long timescales, even neutron star matter eventually decays. Protons themselves might be slightly unstable, decaying on timescales of around 10 to the 34th power years, or even longer. If protons decay, the neutrons inside a neutron star, which are themselves made of similar quarks, may slowly come apart. After a stretch of time so long it cannot really be visualized, the neutron star would gradually shed mass as its constituent particles decay into lighter ones. In the deep future of the universe, long after the stars have all burned out, long after the gas clouds have dispersed, long after black holes have evaporated through Hawking radiation, neutron stars would be among the last solid objects remaining. They would drift in the cold dark, slowly losing the last of their structure until at last even they faded into a thin haze of decaying particles. This is one possible future, drawn from current theories. The exact path depends on physics we have not confirmed. But the picture is clear in one way. Neutron stars are not just dramatic. They are deeply persistent. They were here for the early universe. They are here now. They will be here long after stars stop forming. They will be here long after most things we currently see in the sky have changed beyond recognition. In a universe full of brief, bright, flickering objects, neutron stars are quiet survivors, hot at first, then warm, then cool. Always dense, always strange, tickling our instruments, twisting our equations, refusing to behave like anything we have built or seen. One question remains. Why study them at all? Why pour so much effort into understanding objects so far from us, so different from us? A neutron star will probably never affect your day-to-day life directly. There is no neutron star sitting in our solar system. There is no neutron star aimed at Earth in any threatening way. The next neutron star merger that we might see will be hundreds of millions of light years away. The whole topic might seem distant, beautiful, but distant. There are good reasons, though, to care. The first is the atoms in your body, the gold in your wedding band, the platinum in some car parts, the iodine in your thyroid, the small amounts of uranium and other heavy elements scattered through Earth's crust, all come from somewhere. Many of those somewheres are neutron star collisions. The heavy elements that make up part of your daily life were forged inside events more violent than anything you can imagine, then drifted through space for billions of years before becoming part of the rock that became Earth. To understand where you come from, you have to understand neutron stars. The second reason is the laws of physics. Neutron stars are the only natural laboratories where matter, gravity, magnetism, and quantum mechanics all push their limits at the same time. To study them is to test our deepest theories against the harshest experiments nature can offer. Every measurement we make of a neutron star either confirms what we think we know about reality or reveals a gap in our understanding. Some of the most precise tests of general relativity, the theory that describes gravity, come from observing pulsars in binary systems. So far, Einstein's predictions have held up against every test these strange objects have provided. The third reason is the future of exploration. As humans plan probes that travel beyond our solar system, neutron stars become useful navigation beacons. Their pulses are stable enough to act as a cosmic positioning system. A future spacecraft, leaving the solar system, may use pulsars to know its position in the galaxy, just as ancient sailors used the stars to navigate the oceans. Without our knowledge of neutron stars, that kind of navigation would not be possible. The fourth reason is curiosity. Curiosity is not a small thing. Our species has, in only a few generations, gone from believing the universe was a small dome above our heads to knowing that we live in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies, full of objects more violent and strange than our ancestors could ever have dreamed. Neutron stars are some of the strangest. They challenge our imagination. They give us a sense of scale, of mystery, of wonder. They remind us that the universe is far larger and far stranger than anything we will ever fully grasp. The final reason is harder to put into words. It is the simple, quiet feeling of standing under the night sky, knowing that somewhere up there, a city-sized ball of crushed matter is spinning hundreds of times per second, glowing in X-rays, sending out pulses, slowly bleeding its energy into the dark. The sky is not just a backdrop, it is alive with extreme objects, doing extreme things, in ways that have shaped and will continue to shape our existence. The neutron stars do not need us. They were here long before us, and they will be here long after. But for a brief moment in cosmic time, we have learned how to listen to them, to watch them, to understand them. That, in itself, may be one of the more remarkable stories in the whole universe.